Welcome everyone to the new video in this 885 lecture series, and from today's video we will learn about timing diagrams. As the name suggests, timing diagram. This means we need to draw time, means how much time can be taken by an instruction to be executed. We have to make a diagram of that. What is an instruction? Obviously, instruction is a piece of code, but in this I want to know. So let's say I have written add B. This means I am instructing my machine to add A plus B and store the result at accumulator. To execute this whole instruction, I need a instruction cycle. Now, instruction cycles can be defined as fetch, decode and execute, right? So, we need certain amount of machine cycles for that. Instruction is a collection of machine cycles. An instruction is a collection of machine cycles. How? Okay, so we know that this is our MUP, this is memory, this is IO. The kind of operations that can be performed is from MUP to memory, memory write, from memory to MUP, MUP read, MUP to IO, IO write, and IO to MUP, MUP read. Always decide this write and read operation according to MUP. Okay. Now, so these four are machine cycles. What is our task in timing diagram is we will given an instruction and we need to specify that what machine cycles are required to execute this instruction, and then we need to draw the timing diagrams of those machine cycles. Okay. Now, what is machine cycle? Machine cycle is transferring one data at a time, or 8-bit data at a time. Whenever in your machine there will be a transfer of a 1 byte data, this means one machine cycle has been performed. Okay. So this was some basic terms that you should know before you learn timing diagram. So let's get started. So here is a chart that specify that what according to the machine cycles how a signal is going to work. So IO/M bar, RD bar, all these 5 you know them. I've already discussed them in my architecture video. The new term is here is T states. Actually, this is also not new term if you are a student in computer science or electronics, whatever. What is T states? T stands for transition, right? We human work according to the clock. We know that probably from this time to this time, this time gap is 1 second. Then again the clock will go on, and this is how we measure time. But inside the MUP always gets triggered. After every operation, it again needs to get triggered. Okay, so this is called as a whole T state. Okay, transition states. Now, as you can see, the opcode fetch one, I will discuss it later. First, let me cover these 4. So let's start with the easy one, memory read. Memory read is a memory operation. This means that we are performing M bar. Now, as it's active low, so this will go as 0. It's a read operation, active low, 0. It's a write operation, no, but active low, this is why this is 1. Now S1 and S0, though they are not pronounced as S input and S output, but for our sake of convenience we name it so. So when it's a memory read, means the mu p is reading something. So means that the something is coming. It's a input operation. This is why S1 is true. Obviously, if S1 is 1, then S0 or S output is 0. Memory write, again memory operation. This is why it's a 0. It's a read operation, no, it's a 1. Write operation, yes. For active it's 0. S input, no. S output, yes. First, same as input read and input write. Now, how these T states are being calculated? Okay, let's see. Memory read means, suppose I have some data in my memory. Now my processor wants to read that data. How many clock pulses do we need, or how much time do I need to perform this machine cycle? First of all, we know that this is your mu p, this is your memory. Within the memory there are 64 kbs of memory, so they are 65,636 or something. There are so many memory locations. So first T state is when the address is given by PC. Program counter releases the address, and now first that address needs to be located. For that, one T state is required. On second step, remember whenever we find some this thing that we have a location. Now we need to know whether I will perform write operation or read operation. So this is why control signal is needed. This will also take some time. This is why my next T state is required. And the last T stated, suppose I have taken the example of memory read, right? So my data, so on first T state, PC releases the address. Second T state, I know it's a read operation. Now third T state, there is this data, I need to capture this put into the mu p, and then store it in whatever register it is instructed to. So my last T state is for data transfer. Okay, so this is why 3 T states are required in all these machine cycles. Okay, but here comes the tricky one, opcode fetch. So you may ask that in the previous diagram we have seen about these 4. So from where it comes opcode fetch and all. If you remember, I have already discussed in the addressing mode videos. Any instruction is of 2 parts. Suppose MBI A, 05H. This is the opcode. This is the operand. I'm sorry. Now for opcode, there are 74 unique opcodes, I guess so. For opcode, not for MBI A, this is the opcode is for MBI any register. There will be a specified opcode, and this data that can be whatever, right? That is not unique, but each opcode has a different combination. So in my instruction, when I have to, the instruction I have already discussed you, that instruction is about fetching, decoding and executing. So when probably this instruction occurs, first I need to fetch this from memory. Now this instruction is divided into 2 parts, opcode, operand. This specific, this unique code, this opcode, the fetching of this opcode is known as opcode fetch. Whatever programs you have written, it is stored in memory, and then the MUP performs all the tasks. Obviously it instructs to. But here we have to understand something. First of all, okay, let's just first fill up the line. Opcode fetch, it's a memory operation or a IO operation? Obviously memory, because the opcode is stored at memory. MUP needs to read from them. So 0. It's a read operation? Yes. It's a write operation? 1. S input? 1. Is it output? No, 0. Now can you see opcode fetch and memory read? Both looks the same. But are they the same? Of course not. They are quite similar, but opcode fetch has something else to do also. What is that? Okay. Let's say this example I have taken. For opcode fetch, probably I have the opcode of MBI register. It's 3A. So this is your PC, PC plus 1, PC plus 2, 3A. It's a 2-byte instruction, right? 1 byte for this, 1 byte was this. Only in one memory location we can store 1 byte at a time. So 3A, and on next it's a 05H. This is my opcode, this is my data. Now I am MUP. First step, fetch the opcode, OF. Whenever we fetch an opcode, what happens? First, that opcode gets stored at instruction register. Then it goes to instruction decoder. Here comes the difference. Decoding is understanding the opcode. If we want to execute an instruction, first I have to understand, right, that what I have to do. I mean what the MUP has to do. And what is decoding? Understanding the opcode. So opcode fetch requires an extra machine sign, requires extra T state for this. Obviously the first three T states are same for all. But in opcode fetch, okay, let me just do this again. For the first T state, the address is given by PC, go to 1T, then control signal, okay, it's a read 2T, then it's a 3A, I have to get this data, number 3T, come to MUP, and now get decoded. For that 4T states. After the opcode fetch gets executed, then only MUP understand what is my next operation. And in this we have to perform a memory read operation. So did you understand what is the difference now? Opcode fetch is same as memory read with an extra step, that is decoding. Okay. As both of them looks like the same, this is why scientists identify this as 1. Okay, so now students get confused that S1 and S0, like S input and S output, how they can be same, right? It can't possible. Now, as you know, this is not S input or S output. These are status signals, and for each machine cycle we have a unique pair of combinations. So for S1 S0, for opcode fetch, if both of them are 0, 1, 1, then it means that there is an opcode fetch operation. Okay, so in opcode fetch, how many T states are required? 4T. Now there are some exceptions. Okay, in all the 74 instructions, only a handful of them there are exceptions when we need 6 T state. 4 to 2, 60. I will discuss them if it's needed, but as of now, only for MCQ questions, you should know that Opcode fetch, these states are from 40 to 60, but like you don't let it bother you, because in most of the cases it only requires 40 states. Just for some exceptions, we required 60 states in Opcode fetch. So now do you understand what is happening? First we fetch the opcode, it gets decoded, and then the MUP understand whether I have to perform a MR, MW, IOR, IOW. And this is how the machine cycles works. Next, I'm teaching you how to draw machine cycles for this each combinations, and then I will give you some examples. What do you have to do? Just sum up them. Before I get into drawing the machine cycles, first I need to discuss this important topic. You know that data bus in 8085 is a 8-bit data bus, and the address bus is a 16-bit. So to reduce the number of buses and also size of MUP, there is a facility in 8085 that those 16 buses, or these buses A0 to A15, are divided into two parts. A0 to A7, this carries lower order memory address, LOMA, it's a short form, okay? And the next one is A8 to A15. This is higher order memory address. Now, this A0 to A7 is also used as data bus, D0 to D7. So the first 8 buses, they are AD0 to AD7. They can carry both, either address or data, but the higher order memory address, they are always carrying address. So how can we understand that whether it's address or data? This can be this can be identified by using a ALE, address latch enable. When your ALE is 1, this means now the buses are carrying address, and when your ALE is 0, means the buses are carrying data. I hope I'm clear. Let's understand from the diagram that how this actually works. It's 885 MUP. Now don't get tense to see this. This is just a latch I mean, it's probably a special version, or any company model they use it as 74373. This is a standard number in most of the books. This diagram of latches are used, so I'm also using this one. So this is a latch. It's a 8-bit latch. This is ground. So what is latch? They are a collection of D flip-flops. D flip-flops are used to store a bit. So just know this, that latch will store something. Okay. So how this is working? First, when ALE is 1, suppose at initial stage ALE is 1, means this gate is, okay, just wait, this is 1, gate is opened, means now within this bus A8 to A15, the address is going. When this is 1 and it is coming into this latch, this 8-bit address gets stored here. Am I clear? This will get stored, and now this will only release this A18 to A15. Now when this goes 1 from 0, this gate gets closes, and now when the next data is coming, 8-bit data is coming, this can't get entered in this latch. So what it will have to do, this will just come outside as D0 to D7. Did you understand? ALE is 1, gate is opened. I get my address and it is stored in latch, so now it will just produce the address. Then my ALE goes low, this gate is now closed. Whatever 8-bit is coming, this can't get entry in this latch, so it will just come out as D0 to D7. So I'm getting my address also, I'm getting my data also. And the higher order and memory address, this is just working as it is. There's nothing to do with this. Do you understand? So this is why ALE is 1. This is used for address. When ALE goes 0, this is used as data. Now let's draw some machine cycles. So the first one is opcode fetch. How many T states are required for opcode fetch? 4. So first start from this clock T1, T2, T3, T4. And I think you, as of now, you also obviously know that in 8085 the clock pulses works at 50% duty cycle. So 50% up, 50% low. So you don't have to be like accurate in this, but try to draw as specific as can be, that it shows 50% duty cycle. So this is your clock pulses. Now if you need, just take the help of this chart, okay? I still need this. First, let us saw ALE. I need my address for anything. For any in the T states, the first T states is getting the address, and address is in 16-bit the address bus. This is why we have 2 separate buses. What happens here is a little bit tricky, so please concentrate. First, ALE goes high. When ALE is 1, this means it carries address. ALE goes 1, we have lower order memory address, and A8 to A15, they are carrying the higher order memory address. Okay, first, this T4, it's not something to do with you. This is for decoding. So in this case, we don't have to do anything. We just have to focus on these T1, T2 and T3 part. Okay. For 3 T states, the higher order memory address is carrying address only. But in the case of AD0 to AD7, first I need to carry address and then data. So how it's going to happen, I have just shown only in 1 T states, ALE goes high. This means this will carry address. Then ALE goes low and it continues to do so. Why is this happening? Or why when it's go low, it's carrying data? How it is happening? Look at this diagram. ALE goes 1. The address is coming, gets stored, and now this is only releasing address. Then when ALE is 0, get is closed, and then we will only receive data. But whenever we are getting data from this is continue to do so. Address यहाँ पर आ ही रहा है because it is already get stored, or for the next 3 T states, address is coming from these buses and from them data. So in T1, T2, T3, the lower order memory address is what should I say? We are getting the LOMA for the next 3 T states. because of we are using a latch, it will release these bits for the next 3 T states. But we are not drawing, we don't draw this here. We just show that this is LOMA for 3 T states, and then when this go lower, this will carry data. Now you can ask me that what is this? I will tell you. So for opcode fetch, first this will get high, it will get the address, this will go low, and this will get the data. This is how it executes. And A18 to A15 for all the 3 T states, it is carrying the higher order memory address. Now opcode fetch, it's a memory operation, so this go low. It's a input operation, this go high. Sorry, for S1 and S0 opcode fetch both are high, so this is why high. And then it's a RD bar, it's a 0. Here comes the tick point. We know for the first T stage we will get the address. When will we receive control signal? In second T state. So RD bar, first it is deactivated. Then after the first T stage has gone, means we found the address, then it will take some time to release the ready signal. So when RD bar goes low, means suppose this is your MUP, this is your memory. When we are performing a read operation now, the the PC releases the address, it will get located. Now it will send RD bar signal, and it specifies that we have to read some data. Now the time that is required, see, this is not starting from there, this will comes from there. When RD bar goes low, only then it is carrying the data. So this is the cause and this is the effect. This is called as propagation delay, because in read operation we have to read that data from that memory, so this will also take some time. Okay, so this is called propagation delay. This only happens in read operation. Why in not write operation? Because in write operation we MUP already have the data. It will not waste any time to find that data and all. MUP already have the data, is just specify the location and put that data into it. But in read operation we have to fetch the data from the memory. Okay, so in read operation this will comes. Now the read operation, it needs to finished. I mean, whenever the read operation will get finished, only then the next instruction is going to execute. In the third T states, the data will get stored, right? So we have to stop reading the data and now store it. So before third T states, the RD bar goes high again, and this gets stopped. The data also receive the data, it will send into the MUP, and this will also stop after some time. Okay, so let's have a quick recap. CLK T1, T2, T3, T4 with 50% duty cycle. A5 and A18 for 3 T states, it will carry the higher order memory address. ADA0 for first T states, it's LOMA, but actually it's carrying that LOMA for 3 T states, but we can't show this like this. It will just give a untidy diagram. But now you know, right, that because of that latch we are getting the address only for these T states, but we have to show that we are getting the data also after some time. This is why how this is the diagram works. Then data ALE, first it will get high and then low. For 1 it's address, for 0 it's data. And this is also, I'm not discussing it anymore. And RD bar, obviously for first it is deactivated, then when the address gets specified, this signal will get after the decoding, this signal will get released, and then shouldn't use the word decoding. Decoding is on the last T states. when the opcode fetch is coming. So when the address gets located, then control signal will get released. So this is why it gets needs some time. This is why it is known as propagation delay also. And then we will receive the data and WR bar. Okay. Then memory read. I've already told you that opcode fetch and memory read both are kind of same. Just in opcode fetch we just need an extra T state for decoding, but in memory read that doesn't work. Other the rest of them, they are just same. Okay, so in clock T state T1, T2 and T3, because memory read needs 3 T states, and obviously the higher order address data both buses ALE, IO/M bar, S1 is 0, all of them are the same as opcode fetch. So if you master opcode fetch, then you will also know the difference in memory read. It's as simple as that. And then memory write. Clock pulses T1, T2, T3, ALE. This is just same as before, just as it's a write operation. So this is why only in that signal there will be some differences. Or okay, so memory operation, obviously it goes low. It's a write operation, so S1 is low, S0 is high. It's a write operation, so RD bar is obviously high, and the same as the previous one. In here also, the WR is deactivated at first. Then when the address get located, this goes low, and this means that put that data. Sorry, write the data. Now for the rest of the T states, it will release this signal, and then it has to stop so that the data carries the data also. We can fetch that, and then this gets over. Now do you remember, in write operation the memory already has the data, so it doesn't have to wait. This is why no propagation delay is happening there, because I already have the data. The MUP has to give it to the memory. Okay, so when write bar goes low, this means now carry data and send it. This is why there is no propagation delay or something. Okay, so let's have a quick recap. CLK T1, T2, T3 with 50% duty cycle. ALE goes high, LOMA goes low, data. This is always carries address. It's a memory operation, this is why active low 0. It's a write operation, 0, is output is high. It's a read operation, no, this is why it's high. And it's write operation, yes. Now many of the students can ask that why write operation is not low from beginning. So there are two reasons. First, I have to get my address. That will need some time. The T1 is for that time. This is why in this T state, it is already taking some, this is already deactivated. And then if W bar is already activated, means now suppose my MUP doesn't release the address yet. There is some data, or maybe if I had to read some data, I don't know the address yet, but my W bar is already low. Means MUP is telling me to write something, but I don't know where to write. So what will happen? This data can go to a wrong location also, probably the previous location which was already stored. Probably you have some instruction, we don't execute the temp from beginning, the WR bar goes low. So I just don't know whether the address is, as I can see there is WR bar, I will just write my data at anywhere and it will messed up. In read also, if from beginning it was low, then I don't know from where to read the data. This will ends up giving you garbage value. This is why after T1, this will take some time to go low, and then we can read our data. So this is opcode fetch, memory read and memory write. I'm not drawing IO read, IO write also, because obviously the only difference is in this part, right? And only a child can also do this. When it's IO, this means IO will go low, sorry, IO will go high, and whatever happens, read or write, you can, I'm sure that by now you can draw these diagrams. This is as easy as that. So opcode fetch, memory read and memory write. I've taught you these three. I hope the rest of the two you will learn it yourself, because it's already discussed. Okay, so now the only difference is in IO read and IO write is when we are performing a memory operation now, a memory is of 16-bit, but in IO it is the 8-bit address. I'm sure you have watched the last video. So for higher order address bus and lower order address bus, they carries the duplicate address, because the address is of 8-bit. A0 to A7 and A18 to A15 both will carry duplicate addresses. Okay. Now in many universities it is just like written as you have to get the data 50 from location 4000 and now populated. How it will happen? Okay, so this is lower address. Just a minute. Higher bit higher address, lower bit lower address. So 4000 and the data 50. This is how in some universities it's also asked that maybe they will give you some example and then you have to look. I need to be a little bit more specific about the opcode fetch diagram. I think I've missed this point. In opcode fetch, the T4 is for decoding. This is why we don't have to do anything with this, but also in exams you have to draw this, right? So how in A8 to A15, for the first 3 T states it will carry the address, and for the last one it is unspecified garbage value. This will carry anything, that doesn't matter. And in AD0 to AD7 this will not carry anything. Area that will go low, it will not affect the MUP or any operation. The remains are also same. I just want to specify this one, that this is unspecified and this will also. Now there are some reasons why this goes low, because of the high impedance state. That will not bother you. You don't have to get you don't need to know in so much detail now. So just know that this is unspecified and this will not carry anything. So this is what for opcode fetch. Now let's see some examples. In exams we are given some instruction, like here I have given you MBI B, 10H. You have to specify that which machine cycles will required, and then after you know, you just have to draw them one by one, T1, T2, T3, T4, T5, T6, like for something opcode fetch, then memory read or something like this. So for first of all we have to know that the size of the instruction, then you can understand then in how many locations the instruction will get stored. MBI B, 10H, it's a 2-bit instruction, 1 byte for opcode, next byte is for data. So in memory, in first location, it's suppose XY, okay, the I have the opcode of MBI B, MBI register, and then it's 10H. First draw this. Now how this will get executed? First MUP will fetch this, which is opcode fetch. Obviously one machine cycle opcode fetch will obviously happen. Only then you can understand what will be your next move. So this first opcode fetch is happened, then it decodes that I have to get the data into B register. Then there will be the another machine cycle which is MR. So how many machine cycles are required to perform this instruction? First opcode fetch and then memory read. So how many T states? 4T and 3T, 70. Okay. Next is LXI B, 2008. LXI B 1 byte, then 2000, it will get 00 and 20, right? Higher bit higher address, lower bit lower address. So first opcode fetch, then it tells that I have to get the 16-bit data in BC register. So 2000, as it's a 2-byte number, we have to perform the operation twice. Okay, first opcode fetch will happen. After decoding, it says that fetch these two data also. So from reading something from memory is known as memory read. Again we need a memory read. Sorry. Okay, so how many T states are required here? First, at 3 memory location they will get stored. First opcode fetch, obviously, then get this data from 2 memory locations. So MR, then also MR. Okay. Next is LDA 2000, means load accumulator. It says that we have to get the data from location 2000 into accumulator. So first, if I draw this LDA 2000, it's a 1-byte instruction. Sorry, LDA 2000, it's a 3-byte instruction. Sorry for my mistake. LDA 2000, 1 byte, and then this is 1 and 1, total 3-byte instruction. Our instruction will happen in 3 stages: fetch, decode and execute. So first, when LDA 2000 is here, first what you have to understood, what is the task. Accumulator will get the content of location 2000. Okay, first of all, draw mu p memory I think you can see now. First stage is fetching. So LDA, suppose this is P, PC plus 1, PC plus 2. This for LDA the opcode is probably XY. Just assume that this is XY. First mu P will fetch the opcode. So first step is opcode fetch. After fetching is done, now in the decoding state, mu P understand that I have to get the data from location 2000H. But for that also I need 2000H. Okay, so I have to fetch this 00 and 20. When mu P is getting data from memory, then it's a memory read. So OF MR. Now this gets 2000. We get this address. Now what it is saying? Go to address from location 2000H. Go to this address, and I need the data stored here. Again, what we are doing? We are getting the data from the memory location 2000. So again it's a memory read. So these machine cycles are needed. I will repeat once. LDA 2000. Get the content of location 2000. First step, fetching. Opcode fetch, done. Then I realized I need the data from location 2000. But first I have to fetch these 2 bytes from memory. So it's a memory read. Now I want the data from location 2000. So from 2008 again I need my data, so again it's a memory read. Okay, so total how many T states are required? 4, 3, 3, 3, 6, 13. Total 13 T states are required in LDA 2008. I mean LDA any address, not for 2008 there will be a specific opcode LDA 2300 3000H for another opcode. This is not how it works. You obviously know by now, right? So the opcode is unique. It's for the syntax LDA. There will be an opcode for LDA. Now whatever address comes, it doesn't matter. Next is STA 2000. What the difference between LDA and STA? In LDA, we are on the execution step. We know that I have to get the data from location 2000H. Here what you have to do, first it's a 3-byte instruction, so PC plus 1, PC plus 2. For STA, let's say XY is the opcode 0020. This is my mu P. First fetching is over, OF. So first machine cycle is OF. Then after this decoding, we understand that after that I need my 2000 to get stored. So first 00 and 20 they will get read from location. So this is why MR plus MR, and on the last stage store the data in accumulator to location 2000H. So in the execution step, what I have to do, I have some data in my accumulator, suppose 03H. I need to store this at location 2000H. So when we are giving some data, then it's a memory write operation. Then this data will get stored at this. So first fetching is over, then the address MR is over, and then in execution step we know that I have to give this data into a location. So this is a memory write operation. Okay, so my next instruction is LHLD again it's a 3-byte instruction. So PC plus 1, PC plus 2, whatever 0050. First we have to understand what this instruction does. H and L, 5001 and 5000. The data from location 5000 will get stored at L. The data from location 5001 will get stored at H. Okay. First step, fetching. Mu P fetch is it OF. Fetch this to MR. So OF plus MR is done. As OF done means decoding is also done, and decoding says that I have to get the data from these 2 locations. So the next step will be from location 5000 I need my data into L. So again there will be a memory read, and from location 5001 I need another data in H. So again there will be a memory read. So how many T states are required? OF of this opcode fetch. When fetching is over, means when fetching is over, that decodes that I need these two that I need the data from these two addresses. So but as the instruction says, first I have to get these also, mr plus mr, and then as per decoding I need to get this data mr plus mr. If it was SHLD, only the last two will get changed. For obviously for the first 3 t states, of course obviously all are same, and then when it's stored store HL pair means I have to put the data in these two locations, then it will be MW plus MW. Okay, so how many t, so how you will write this? First for opcode fetch T1, T2, T3, T4, then MR, T5, T6, T7, MR, T8, T9, T10, MW. This is how you will draw them. You know how to draw opcode fetch, memory read, memory write. First just identify how many machine cycles will get required and then just sum up. Okay. Moving to the next example, which is add B. It's a 1-byte instruction. When B memory add B, opcode fetch is over. This says that when it is getting decoded, that add these A plus B and store them in A. Where is accumulator? Inside the MUP. So does it need any memory or any IO operation? No. Whatever execution is happening, it is inside the MUP. So add B, this is just only one machine cycle, which is opcode fetch. Then the instruction gets executed in the MUP itself. So this is why no further in machine cycle is required. Just like when there is I, in the previous examples, MBA 05H, this is immediate addressing mode. Means whatever is happening immediately inside the MUP, we don't need to get out of there then. I mean, there will be only, the operation is, I have to get the data in A register. So only after memory read, there are no further steps required. It's immediate addressing mode. Everything happens there inside MUP when. Okay, so this is another example. I'm getting off topic. So what we are discussing is add B. So opcode fetch, then only it understands that I have to, whatever operations are being performed is only inside the MUP only. So this is why only one machine cycle is required, which is opcode fetch, means 4 T states. The last one for today, and probably the trickiest one. This often comes in exam. In most colleges, there the example that comes is MBI register comma data, but INR M. This one is a bit tricky, and I love this instruction. What is M? M holds the data pointed by HL pair. How this instruction will get executed? First of all, obviously, opcode fetch OF. Fetching is over. In decoding, it says that you have to increment the data that is stored at the location pointed by HL pair. So first I have to get the data, okay, probably in HL, the address was 3000. So according to my decoding, I have to get the data from location 3000, suppose 05H. After fetching is over, when decoding is also over, we understand now it's time for execution. For execution, I have to get the data. When we are reading something from memory, that's a MR operation, right? 05 comes here, accumulator increments it, now it becomes 06. Now, this data needs to get changed also. This is what my instruction says, right? I have to increment the data. So from this 06 has to get stored here. So when MUP is giving data to memory, this is memory write. Do you understand what is the point? When we are doing some, suppose ADI 05 means A plus 05 gets stored at A. So when opcode fetching is over, this data is also come, OF come, MR comes. Now whatever is happening is only inside the MUP. The execution happens inside the MUP. No further any machine cycles are required. But in INR, opcode fetch is over for this data, memory read is over, and then I have to, after incrementing the data, I have to change this. So this is why the another machine cycle that is required is MW. So in INR, OF plus MR plus MW, 4 plus 3 plus 3, 10 T states are required. This was it for today. Thanks for watching. If you need any notes, you can mail me, or if you have any query, please ask me in the comment section. Thanks for watching. Do subscribe.